Hi, and welcome to week 4 of Practical Bayesian Methods. This week we're going to cover the Markov chain Monte Carlo, which is kind of a silver bullet of probabilistic programming, because it allows you to train or to do inference on almost any model without too much trouble. We'll discuss some extensions of this technique, so how to make it faster on some particular problems by exploiting the structure of your problems, and we'll also discuss some limitations, like the speed of the method. So let's start the discussion of Markov chain Monte Carlo with the Monte Carlo part. Monte Carlo was originated in the Manhattan Project, which gave us the atomic bomb. It was a quick and dirty answer to the question what to do until the mathematicians arrives. The idea of Monte Carlo simulation is so if you have a complicated model of some problem and you want to predict something about this model, instead of thinking carefully and writing down equations and solving them, you may just simulate your model lots and lots of times and then see, for example, the average of this simulation as some kind of smooth prediction of what will happen. So probably the reason why this thing was invented in Manhattan Project is because it's one of the first really huge scientific projects where we already had lots of needs to approximate integrals and do this kind of simulations. And second of all, we already had computers in some reasonably useful state where we can actually simulate stuff not manually but automatically. And the Monte Carlo algorithm turned out to be pretty efficient, and it made it to the list of top 10 inventions of top 10 algorithms of 20th century. So the name Monte Carlo was given by the name of the city Monte Carlo, which is famous for its casinos, and probably because everything in Manhattan Project had to have its code name. So let's see a small example of what I'm talking about. So what is Monte Carlo applied to some really simple problem? Say you want to approximate the value of pi. And you know that pi is the area of the unit circle with radius 1. So we can kind of use this information to approximate it. And the idea here is that if you consider a rectangle with from 0 to 1 on both axes, then this quarter of a circle which appears in this rectangle has exactly the area pi divided by 4. It's just 1/4 of the circle. And its area equals to some integral which basically says at each point whether this point is in the circle or not. So if we integrate this thing along this rectangle, we'll get the area. So how can we compute this integral? It's hard, but we can throw lots and lots of points on this unit rectangle and just see the fraction of those points that appeared in the circle, in this quarter of the circle, and use this as an approximation to what the integral really is. So you can see that this is maybe not the best method to approximate the value of pi, because here, for example, you spent like 3,000 samples. So you sampled 3,000 points, and the p was approximated as 3.1, which is not the best accuracy you can get with this much computations. But anyway, the method is really simple. It's like 2 lines of code in almost any programming language. And this is the general theme of Monte Carlo simulation. So Monte Carlo usually gives you something which is really easy to program, which is really universally applicable to lots of problems, which is very scalable to parallelization. So if you have like 100 computers, then you can really easily parallelize this thing to be 100 times more efficient, which is not the case for many other algorithms which are much harder to parallelize. And sometimes these Monte Carlo methods can be slow compared to other alternatives. So usually, if you sit down carefully for a week and like write down lots of equations and think, then you may came up with a better way to solve your problem than to do just Monte Carlo simulation. Sometimes not, but sometimes it's just a quick and dirty approach which gives you the first approximation. But anyway, it's very useful. So to be a little bit more general about this family of techniques, let's say that we want to approximate some expected value of some function f with respect to some distribution p of x. And we will sample a few points, for example m points from this distribution p of x, and use the average of f of xi's as the approximation. So here we're kind of using sampled average instead of the expected value. And this thing has lots of nice theoretical properties, like it's unbiased, meaning that if you sample enough points, you can get closer and closer to the actual true answer, at least with high probability. And anyway, there are some guarantees on how fast you will converge to that. So this is Monte Carlo. And you may ask a question like, why do we care? Why do we need to approximate expected values? Well, in probabilistic programming, there are probably a few reasons to do that. Let's consider two of them. So first of all, if you're wanting to do full Bayesian inference, like we covered a little bit in week 1, then instead of having some parametric model and finding the best value of parameters, you may just want to treat your parameters as latent variables. And then for a new object x, if you want to predict its label, for example, and you have some training data set x-train and y-train, you may want to just integrate out this latent variable, like this. So imagine that, for example, x is an image, and you want to predict like whether it's an image of a cat or a dog. And then p of y given x and w, maybe for example a neural network with weights w, and which takes as input this image x and outputs your distribution over labels y. And then instead of using this just one neural network with some kind of optimal or best set of weights w, you're considering all possible neural networks with this architecture. So for each possible value for weights w, you consider this neural network, you pass your image through this neural network, you write down the answers, the p of y, and then you average all these predictions with some weights, which are given by the posterior distribution and the weights p of w given the training dataset. So it's like an infinitely large ensemble of neural networks, where the weights of the ensemble are given by the posterior distribution p of w given the training dataset. And this p of w given the training dataset gives you some idea about how well these weights will behave as a weights for your neural network. So it will this value will be higher for reasonable weights and lower for the weights which doesn't make sense. So this way, you're doing full Bayesian inference. You're having a few benefits of probabilistic modeling, like you can, for example, predict uncertainty in your predictions. And well, basically, instead of just fixed value of weights, you have distribution over weights. And this thing is, of course, interactable. So if you have a complicated function like a neural network here, you can compute this integral analytically. So you have to do some approximation. And one of the way to do it is to just say that this thing is just an expected value of this neural network. So we have a neural network output, and we're computing the expected value of this neural network output with respect to some distribution on weights. And so we can approximate this thing with Monte Carlo, if we can sample from p of w given the training dataset. So this is one example where the Monte Carlo can be useful to approximate expected value in the probabilistic modeling. And you may ask, like, how we can find this posterior distribution of the weights, p of w given the training dataset. Well, as usually, the posterior distribution is proportional to the joint distribution, so likelihood p of y train given x train and w times the prior on w, and divided by some normalization constant. And so the numerator here is easy, because you defined your model yourself. You could have, for example, defined p of w, the prior, to be normal, and the likelihood is just your output of your neural network. So you can compute this thing for any values of y, x, and w. But then the denominator, the normalization constant z, is much harder. It contains some integral inside, so you can't ever compute it. So it's kind of a general situation where you know your distribution from which you want to sample, but only up to normalization constant. Okay? And other example of where this kind of expected values approximation can be useful in probabilistic modeling is the M step of the expectation maximization algorithm, which we covered in week 2. So on the E step of expectation maximization, we found the posterior distribution P of latent variable t given the dataset and parameters. And on the M step, we want to maximize the expected value of logarithm of the joint probability with respect to the parameters theta, and the expected value is with respect to this posterior distribution Q. So here again, if the posterior distribution Q is too hard to work with, and we can't integrate this thing analytically, we can do a few things. First of all, we can approximate Q to be to lay in some simple class, like factorized distribution. And that's what we did in the previous week 3, about variational inference. So we are approximating the posterior and then computing this integral analytically for this simplified posterior. Or we can use the exact posterior, but we can sample some dataset of samples from this posterior dataset of latent variable values, and then approximate this expected value with just average with respect to these samples, and then maximize this approximation instead of the true expected values. So these are two examples of where you can need expected values in probabilistic modeling, and how Monte Carlo simulation can help you here. And in the following videos, we are going to use the formulation of this problem as we want to learn how to sample from a complicated probabilistic distribution, which we know up to normalization constant. And we will always write like P of x, meaning that x is the parameters you want to sample. So here we had, in the first example of full Bayesian inference, we had P of w given some data. And in the second example, we have P of latent variable given some, again, data. But in all cases, in the following videos, we will just write down, P of x, meaning that it's some distribution we want to sample from. In this video, we're going to cover sampling from one-dimensional distributions. And let's start with the simplest case, a one-dimensional discrete distribution. So say we have a random variable like this, which takes the value of A1 with probability 0.6, value A2 with probability 0.1, and the value A3 with probability 0.3. How can we sample from it? Well, we have to start from something. It's hard to generate randomness from nothing on a deterministic computer. So we're going to use this kind of function which can generate your random number on the interval from 0 to 1. And this function is included in almost any possible programming languages or library. So it's usually there, and we can use it to base our further sampling techniques on it. So but anyway, we have this function. How can we generate a sample from this discrete distribution? Well, let's start with the interval, and let's decompose it into 3 chunks, where the first chunk has length 0.6, the second chunk has length 0.1, and the third chunk has length 0.3. And let's say that we're going to generate a random number on this interval, and let's say that if it appears in the first chunk, in the red one, then we will say that we have just generated the value of A1. So let's generate a random number from our function, which just throw a random point on this interval. And let's say it appeared to be somewhere around 0.9, for example. It means we have just generated the value of A3. So why does it work? Well, because obviously if you throw a random point on an interval, then the probability that it appeared in some chunk is proportional to the length of the chunk. And the length of the first chunk is 0.6, which is exactly the probability we wanted to A1 to be generated, and etc. So this indeed is a correct procedure for generating random numbers from discrete distributions with finite number of values. And the bottom line here is that it's really easy to generate discrete distributions, generate samples from discrete distributions. But note that here we had just 3 values. If we, for example, had 1 million values or 1 billion values, it would be much harder, because we would have to spend amount of time proportional to 1 billion to separate this interval into 1 billion chunks of appropriate sizes, and then to find in which particular interval, in which particular chunk the random value appeared. But if you have finite number of discrete events, and this number is not that large, it's like 1000, then you can really efficiently and easily generate samples from this distribution. Okay, let's move to continuous distributions. So let's say that for beginning that we want to sample a point from a Gaussian, like this. How can we do it? Well, one idea is to use the central limit theorem that says that if we have a few independent random values, and if we sum them up together, we'll get something like Gaussian. So if we just throw, say, 12 random numbers from the uniform distribution on interval from 0 to 1, and then add them all together, we'll get something with expected value being 6, because, expected value of each xi is 0.5, it's the center of the interval, and the sum of 12 xi's will be from 0 to 12, and the center of this interval is 6. So we have to subtract 6 to make the expected value of this distribution to be 0. And this way our distribution will be actually not from minus infinity to plus infinity, like in the Gaussian case, but rather from minus 6 to 6. So it's indeed an approximation. It can't generate you anything like an actual Gaussian, but it's a pretty close one. So although it cannot ever generate you, for example, a number of 100, but the Gaussian itself is also very, very improbable to generate you 100. So you can be okay with this, with losing these highly improbable parts of your sample space. And you may ask, why 12 here? Well, it's just to make the variance of the resulting random variable z to be equal to 1 as of standard Gaussian. If you use, for example, not 12, but I don't know, 100 values, you would have to divide this thing by something to make its variance to be 1. Or if you don't want to use these kind of loose approximations, you can ask your favorite programming language for a function which just generates you numbers from Gaussian, and it probably has it. So it's a pretty standard thing to have in a programming language, to generate numbers from a standard Gaussian. And this is kind of more efficient and more accurate than just, generating it from central limit theorem. So okay, Gaussians are easy. But what if we have a more complicated distribution, like this, and we don't know how to sample from it? Again, as we discussed in the previous video, it can happen if, for example, this is a posterior distribution on some parameters or some latent variables, and we may even know it up to normalization constant, not exactly. So what to do in this situation? Well, we know how to sample from Gaussians, so let's try to use it. Let's upper bound our distribution with some Gaussian times some constant, for example 2 in this example, because it's impossible to upper bound one distribution with another one without a constant, without multiplying it with something. Okay, so we have distribution p of x, the blue curve, which we want to sample from, and we have the orange curve, which is 2 times some Gaussian, which we can sample from. So how can we generate samples from the blue curve? Well, let's start with generating a sample from the orange curve, which we can do. Now we, for example, with high probability can get a number around 0, because it's around 0, it's somewhere there the orange density is high. So there will be quite a few points there. But the blue density is not high there. It's like kind of a local minimum. So we have to somehow correct for this. We have to, for example, throw away some of the points which were generated in this region where the actual blue probability is low. So let's do just that. Let's reject some of the points generated from the orange curve. And what is the rule for rejecting the point? Well, first of all, it should be probabilistic, because you can't just reject all points at some region. Otherwise, the resulting distribution of your accepted points will have zero probability in this region. So you have to reject some of the points in some kind of probabilistic manner. And the probability with which you want to reject the particular point, so point x tilde here, should be proportional to the height of the blue curve and with respect to the height of the orange curve. So if in the current point the two curves coincide, they have the same values, you don't want to reject anything. You are happy to accept the point which was just generated. If, for example, at some region the orange curve is high, but the blue curve is 0, then you don't want to accept anything. You want to reject all the points in these regions. If it's somewhere in between, if, for example, like here we have around 0.7 proportion of the blue curve to the orange one, around 0.7, then we'll expect to keep 0.7, so 70% points in this region from the ones we were sampling. So we can say that we have generated x tilde, which is from the orange curve. Then we generate its y coordinate, which is from 0 to the orange curve at the current point. And then we'll reject this point if it appeared in the red region, where so above the blue curve, and we'll accept this point if it appeared below the blue curve. You may ask, why does it work? Well, if you look at the points that were generated by this procedure before rejecting anything, they will be uniformly distributed under the orange curve. When we apply our rejection procedure, we throw away the points that appeared under the points that appeared above the blue curve and below the orange one. And what is left is the points that are uniformly distributed under the blue curve. And it's kind of natural that these points, their x coordinates are distributed as the blue curve suggests. So that's great. It's a procedure to generate your samples from any distribution you can upper bound with something you can sample from. But how efficient is it? So if you want to generate 1 point, how many points you will have to generate from the orange curve before you accept one of them? Well, the answer to this question is just 1 divided by the constant. So 1/2 in our example, and 1 divided by m in the general case. And the reason for that is just because it's the ratio between the area under the blue curve, which is 1, because it's a probability distribution, and the area under the orange curve, which is m, because it's m times a probability distribution. So if we throw uniformly points in some area and then reject some of them, then the probability of accepting the point is proportional to the area where we accept them. And note that here we can even use this method if we know our distribution up to normalization constant, as it usually happens in probabilistic modeling. So in this case, if you can still upper bound your unnormalized distribution, you can just call this you can say that this constant m, this tilde m, is just includes the normalization constant somehow. So you don't know the normalization, but you can upper bound the distribution with some constant. And this will still work. So as a summary, this method is called rejection sampling, and it's kind of universally applicable. So it's really often then you can upper bound your distribution and generate samples from it like this. But the downside is that if Q and P are too different from each other, then you have to choose large constant m, and then you will have to reject most of the points. And so if, for example, m is 100, then you will, to generate just 1 point from your actual distribution, the blue curve, you will have to generate 100 points, and then on average, just one of them will be accepted. And another problem of this approach is that if you apply it to multi-dimensional case, it will still work, but the normalization constant, or the constant m will probably be very, very large. So it's kind of exponential in the number of dimensions. And it's really improbable that you will be able to upper bound your complicated distribution in 10-dimensional space with a constant smaller than, for example, 1 million. And having constant 1 million means that to generate just 1 point, you have to wait million computational cycles, which is a lot. So this is a method for 1 dimension or maybe a few dimensions, but not like 1,000-dimensional spaces. In the previous videos, we familiarized ourselves with the Monte Carlo part. So now let's talk about the Markov chain part, which is actually a really cool idea on how to generate samples from complicated multidimensional distributions kind of efficiently. So what is a Markov chain? Imagine a frog which sits on a water lily. And this frog have kind of discrete time. So at each time step, and there are, like, at each second, for example, it makes a decision whether to stay on its current lily or to jump to the other one. And its decisions are kind of predefined in probabilistic way. So if it's right now on the left water lily, it will stay there with probability 0.3 and will move with probability 0.7. And if it's on the right one, it will stay or move with probability 0.5, for example. Now we can say that we have kind of a dynamic system, which has a state. So the state will show us where the frog is now. This dynamic system, it kind of evolves through time. Its states changes, and the rules by which the states changes are as follows. So the probability to transition from left state to left state is 0.3, and etc. So you can define the behavior of your dynamic system by using these transition probabilities. So we can simulate our dynamic system. We can say that, for example, on the time step 1, the frog was on the left, and then maybe it jumped to the right on the time step 2, and then maybe it stayed to the right, and then maybe it went to the left, and then, for example, to the right. And we can write down the path through the state space which our dynamic system made. So it was like left, right, right, left, right. And this thing is called Markov chain because the next state is kind of depends only on the previous state. So the frog doesn't care where it was 10 time steps ago. The only thing it cares about is where it is now. To make the decision, it just needs to know where what is the state now. Okay, so we can ask ourselves a question, like with where the frog will be after 10 time steps, for example. So let's say that we started from the time step 1 and the frog was on the left. So with probability 1, it was on the left, and with probability 0, it was on the right. What is the probability that it will be on the left or on the right in the time step 2? Well, it's 0.3 and 0.7, right? Okay, and what about the time step 3? It's kind of trickier, because we don't know where it was before. But using the rule of sum of probabilities, we can kind of check all the possibilities for the previous state and use that to compute the next probabilities. So the rule of sum says us that the value of the state at the time step 3 equals to the value of the state of the time step 3, given that at the second time step it was on the left, times the probability that it was on the left on the second time step. plus the same thing considering that the situation that it was on the right on the second time step. And we can, just we know all these values because the conditional probability is just the transition probability. So the probability that the frog moves from left to right, for example, and the prior probability of x2 are computed in the previous line. So it's what we have just computed. And we can write it down. So it will be for probability of the left in the third time step, it will be something like 0.3 because it's the probability of transitioning from left to left times the prior probability of 0.3. So it's from the previous line of the table, plus the probability of the prior probability of being on the right in the previous time step, which is 0.7, times the transition probability of moving from right to right, which is 0.5. I'm sorry, from right to left, which is 0.5. And we can write the same thing for the for being at the right state in the time step 3, and we'll have some numbers like this, which are around 44 and 56. And we can continue this table for as long as we want, and we'll found out that the table kind of converged to numbers around 42 and 58. So after like 1 million steps, the probabilities that the frog is on the left is almost exactly 42, and the probability that the frog is on the right is almost exactly 58. Which basically means that if we simulate our frog for long enough, and then write down where it ended up at the 1 millionth step, then we will kind of get a sample from this discrete distribution with two values. So with probability 42 we'll get left, and with probability 58 we'll get right. So let's look how it works. Say we simulate our frog for like 1 million steps, and the last step was, for example, left. Okay, we'll write down this left, and then simulate another path through the state space. So again simulation, and the last state was, for example, right. We write it down, and by doing this several times, we have a sample from a distribution of the millionth step of our dynamic system, given that the frog started on the left. And this thing will be close to the probability 42 and 58. So even here we can see that where we have like 2 out of 5 lefts and 3 out of 5 rights, which are close to 42 and 58. So this way we can generate it's a really loosey way to generate samples from this discrete distribution with two values. So there is a much simpler way, which we have just discussed in the previous video. But note that this way, so build a dynamic system and simulate it and see where it end up, works even for more complicated cases. So what if you have, for example, 10 lilies or 1 billion lilies? If you want to simulate your distribution by, in naive way, if you have billion values in your discrete random variable, you'll have to spend amount of time proportional to 1 billion to generate one sample from it. If you use this kind of idea of simulate some dynamic system and then write down the last position, and if you do not that many steps, like 1000, and hope that everything has converged to the true distribution, then you can get a random number from this complicated discrete distribution without too much trouble of the naive approach in the billion values example. Or maybe your frog can be even continuous and can jump from any point on your 2D plane to any other point. And in this case, you will be able to generate your samples from a continuous distribution by simulating your dynamic system. So the idea is that you can still sample efficiently, even if you have this continuous dynamic system, by just writing down the path for this 2D plane and writing down the last position. So the idea of Markov chain simulation applied to generating samples of random values is as follows. we have a distribution we want to sample from. It may be continuous, it may be discrete. We built a Markov chain that has this distribution, so that converges to this distribution. Okay. Then we start with from any initialization, x0, and then we simulate our Markov chain for long enough. For example, for 1000 iterations. So we start with x0, then we generate x1 by using the transition probability, and etc. And then we hope that after 1000 steps, you will converge to the true distribution p of x, because we build our Markov chain this way. Then after these 1000 steps, you can throw away the first 1000 samples, 1000 states, and then you can start writing down these states after these 1000 steps, because they all will be from the distribution p of x, or at least close to it, if your Markov chain converges close enough. Okay, so this is the general idea. And in the following videos, we will discuss how to build Markov chain with this property. So how to build Markov chain that converges to the distribution you want to sample from. But let's first discuss a little bit about whether a Markov chain converges anywhere. So in which cases it does converge and which it doesn't. Well, the first observation here is that the Markov chain doesn't have to converge to anywhere. So, for example, if you consider a dynamic system like this, the frog will always swap the lily at each time step. And so if you look at the table, it will look like this. The probability of being on the left on the first time step is 1, and to be on the right is 0. And then you swap things, so you certainly will be on the right on the next time step, and then you will certainly be on the left on the next time step, and etc. And this thing will never converge to anything stable. So it will always swap the place. So this thing doesn't work for us. We want something that converges to some distribution. And the question of whether or not a given Markov chain is converged, is converging to something, is actually pretty well studied. Well, first of all, we'll need a definition of what does it mean for a Markov chain to converge to something in the mathematical terms. So this is something called a stationary distribution. And the distribution pi is called stationary for a Markov chain T if the following equation holds, which basically says us that if you start from this distribution pi, and if you marginalize out the current position x, then you will get basically the distribution over position on the next time step. And this has to be pi again. So basically, if you start from pi, if you sample a state from pi, and then if you make one transition, so one time step of the Markov chain, then the distribution you will get after that is again pi. And this means that if we encounter this pi at any point of our sampling, then we will stay at it. We will not change this distribution. And there is a nice theorem that says us that if the transition probability is non-zero for any two states, so if we can jump from any state to any other one with non-zero probability, then there exists a unique pi which is stationary. And we will converge to this pi from any starting point. So if we build a Markov chain that has non-zero transition probabilities, and that has a stationary distribution which we want to sample from, then no matter where we start, if we simulate our Markov chain long enough, we will get eventually samples from the desired distribution pi. In the previous video, we discussed that it can be nice to build a Markov chain to sample from some distribution. But how to build such Markov chain? A simplest method for that is called Gibbs sampling. And it works as follows. So say we have a distribution, a three-dimensional one, which we know up to normalization constant. So we can compute this probability or density in the continuous case at any given point, but up to normalization. So the gift sampling works as follows. First of all, we start with some initial point, for example, all zeros, and it doesn't matter where we start. Well, it does matter for some convergence properties and stuff like that, but it doesn't matter for the sake of correctness. And then we are starting to build our next iteration point. And we're going to build this next iteration point one dimension at a time. So the first dimension of the next point will be sampled from conditional distribution on x1, given the values of x2 and x3, which we had from our initialization. And you may ask, like, how can we sample from this conditional distribution? It's also a hard problem, right? But note that this conditional distribution is proportional to the joint distribution, so it's we know it again up to normalization constant. And sampling from one-dimensional distributions, it's usually much easier than sampling from a multidimensional one. So we assume that we can do it. In some particular practical cases, we can invent a really efficient scheme for analytically sampling from these kind of one-dimensional distributions. In others, we have to use general-purpose schemes like rejection sampling. But anyway, one-dimensional sampling is easy. So let's go to the next substep. On the next substep, we are going to generate the second coordinate, second dimension of our first iteration point. And it's going to be generated from the conditional distribution on x2, given x1 being the dimension we have just generated, and x3 being the initialization point dimension. And finally, we will generate the third dimension in the same fashion. So we'll generate it from the conditional distribution, given the stuff we have just generated. And in the general case, this was the iteration 1, and these three substeps constitutes into just one kind of big step of our Markov chain. So it's a way we transition from x0 to x1. And if you write it down for general iteration number k, it will look like this. So the point of iteration, the point from iteration k plus 1 is generated one dimension at a time by using some conditional distributions, which are conditioned on the stuff we have from the previous iteration and from the current iteration. And note that this scheme is really not parallel. So each step depends on the previous steps to be executed. And this means that no matter how many computers we have, if we have like 1 million dimensional space, we'll have to sample these dimensions one at a time, which is kind of a downside, but we'll discuss later how can we avoid it. Anyway, this procedure gives you a way to move from x0 to x1, then to x2 and etc. And let's prove that this indeed defines a Markov chain which converges to the distribution P. So if we sample like this long enough, we will get samples from the desired distribution. And we are going to do it on the blackboard. So let's prove that the Gibbs sampling, all the three substeps considered as one big step, indeed provides you a Markov chain that converges to the desired distribution P. So what we want to prove is that P of the new point, x prime, y prime, and z prime, equals, so we want to prove that it equals to the one step of the Gibbs sampling after, so starting from the distribution P and then doing one step of the Gibbs sampling. So here we'll have marginalizing out the previous step, x, y, and z, the transition probability q, probability to go from x, y, z to x prime, z prime, y prime, z prime, and times the probability p. So we want to prove that these two things are equal to each other. Let's look at the right-hand side of this expression. So we have sum with respect to the previous point of the transition probability. So how probable is it under the Gibbs sampling to move from xyz to x prime z y prime z prime? Well, we have to first of all move from x to x prime. So it will be this conditional probability, x equals to y, and z equals to z. Then we have to assume that we moved to x prime, and then what is the probability that we move from y to y prime? So it will be y prime, given that we have already moved to x prime and started with z. And finally, the third conditional probability that we move to z prime, given that we already moved to x and y prime. So this is the transition probability Q, this overall thing, and times the starting probability P of x, y, z. So times P of x, y, z. And we want to prove that this thing equals to the x prime, P of x prime, y prime, z prime. Because in this case, we'll prove that this P is stationary for our Markov chain, and then it means that the Markov chain converges to this distribution P. So, first of all, let's note that this part, P of z prime, it doesn't depend on x, y, or z at all. So we can move it outside the sum. It will be P of z prime given x prime and y prime times sum of these two terms and then times the probability P of x, y, z. And note here that actually the only part that depends on x is this one. So it's P of x, y, z. Which basically means that we can push the summation inside. We can write here the sum with respect to only y and z, and write the summation with respect to x here. So it's summation with respect to all values of x from 1 to the cardinality of x. And also, by the way, note that if our variables x, y, and z would be continuous, we'll have integrations instead of sums. But the overall logic of the proof will be exactly the same. Okay, so we have this expression. These two are equal to each other. And you can note that this part, we have just marginalized out x. So we end up with P of y and z, the marginal distribution P of y and z. Great. Okay. Now we can multiply this part by x prime given y and z to get a joint distribution. So this thing will equal to again this part times sum. We'll have P of, well, let's start with this term, P of y prime given x prime and z, times the product of these two terms, which is the joint distribution. And note that the only part that depends on y is this joint distribution. So we can move this summation again with respect to y inside. And write down here summation only with respect to z, and here the summation with respect to y. So it will be P of x prime and y and z, which is a product of these two terms. Okay. And again, note that when we marginalize out y here, we end up with P of x prime and z. And again, we can multiply these two terms together to get a joint distribution. So finally, we have something like this. It's again the first term, p of z prime, given x prime and y prime, times summation with respect to z of p of y prime given x prime and z times the joint distribution. So it's just the full joint distribution of these three terms, y prime and x prime and z. And this part, since we marginalize out z, again it equals to p of y prime and z prime by the definition of the marginalization. So it's like rule of sum of probabilities. And finally, by multiplying these two terms together, we end up with what we wanted. So this thing equals to p of z prime, x prime and y prime. So we're done here. We have just proven that if you start with the distribution p on the step x, y, z, and then make one step of this Gibbs sampling procedure, one coordinate at a time, we'll end up with the same distribution p of x prime, y prime, and z prime, which basically means that this distribution p is stationary for the Gibbs sampling. And thus we will converge to this distribution from any starting point. And basically it means that if we use Gibbs sampling, it indeed will eventually start to produce us samples from the distribution p. So we have just proved that the Gibbs sampling scheme indeed gives you a correct way of sampling from the desired distribution. So the underlying Markov chain indeed converges to the distribution p. But let's look at a small demo of how it can work on practice. So let's look at this simple two-dimensional distribution, which looks like a Gaussian. And note that we actually don't need Gibbs sampling here, because first of all this distribution is two-dimensional. So the rejection sampling scheme can also be applied here because the dimensionality is not large. And also this is Gaussian, so we can efficiently sample from it without too much trouble of any these fancy techniques. But this is only for illustrational purposes. Gibbs sampling works even in million-dimensional spaces with complicated distributions. So let's start with a point 0, 0, initialization point. So first of all, on the first substep of the first iteration, Gibbs sampling suggests you to find the conditional distribution on x2 given x1 is 0. And it will look like this here. Because if we know that x2 is 0, then x1 should be somewhere around 5 or 6 because of the shape of our Gaussian distribution. It has more points in that region than in other regions for this particular value of x2. Let's sample a point from that. It can look like this, for example. Okay, so this is the first substep. On the next substep, we have to compute the conditional distribution on x2, given that x1 is the one we have just generated. So x1 is 6, or somewhere around there. And the conditional distribution on x2 will be like this. Again, it's just the position of the points where there are more points of our Gaussian distribution lies if their x1 coordinate is 6. So let's sample from that and get a point like this. This is the result of our iteration 1. So this is the next point in our Markov chain process. Great. Note that here we haven't converged yet. So we even didn't found a region of space where the density of our distribution is large. We're somewhere in the low density region. So we can't use these samples yet because they are not from the true distribution. So let's proceed. Next iteration, we again sample from the conditional distribution on x2. On x1, given that x2 is around 1. And this is somewhere here. Okay, let's sample from it, and let's move to this point, and this is the end of our substep 1 of the second iteration. And on substep 2 we will generate a point like this, again from a conditional distribution. So one more substep, and the end of the third iteration, and finally if we repeat this process for like 10 more iterations, we'll get points like this, which are already looks like something from the Gaussian. So this was a demo of how Gibbs sampling works, and to summarize some kind of its properties. So first of all, the Gibbs sampling idea is to, instead of one complicated problem of generating samples from multidimensional distribution, which you may know up to normalization constant, it reduces it to sequence of one-dimensional sampling problems. And this is very nice. It makes everything more efficient. But note that if in the first video of this week we discussed some schemes where we can generate a point and that's it, we have just one sample by spending some time on generating it. Here we have a chain of samples, and they have so you can't generate a first sample unless you, for example, converge. So you have to wait these first 500 iterations and then throw away these first samples to get just one sample that you care about. Another positive feature of this Gibbs sampling is that it's really easy to implement. So it's just a few lines of code in Python, and it's really universally applicable. So almost always you can sample from one-dimensional conditional distributions, and this way you can sample from the multidimensional one. And the negative feature is that it can give you really correlated samples. So if you recall the demo, all samples were kind of close to the previous one. So you can't do large steps here in the Gibbs scheme. You're always doing some kind of local steps because you're going one dimension at a time. And this means that your samples are similar to each other, which in turn means that you're not that efficient in estimating expected values as you would wish. So let's say that we waited for the first 1000 iteration of the Gibbs sampling and throw these points away, saying that this was useless for us because the Markov chain didn't converge yet. And then after the 1001 iteration, we are starting to collect these samples and write them down to use for our expected value estimation. And for example, we may say that we collected 1000 samples. Well, we may think that we have 1000 samples, but they are so close to each other that in fact it's like you had 100, for example, 100 independent samples. So the efficiency of estimating expected values with correlated samples is much lower than the efficiency of estimating the same thing with uncorrelated samples. And this can be a problem. So it's an efficiency problem. One other negative feature is that because of these small steps, it can be hard to converge. The convergence here in Markov chains is sometimes called mixing. So you have to do lots of steps to find this high density region of your probability distribution, and you have to throw all these points away because you haven't converged yet and you can't use these points. So because of these small local steps, you have to wait for convergence longer than you would have if these steps were larger. And finally, as we have already discussed, this method is not parallel, and if you want to sample from like 1 million dimensional space, you have to anyway sample each dimension one at a time, which can be really slow to do. So in the next video, we'll discuss some other scheme for building Markov chains that can be used to mitigate some of these problems. In the previous video, we discussed one way to build a Markov chain that converges to a desired distribution, namely the Gibbs sampling. And we have discussed that it has some downsides. So it produces highly correlated samples, and it converges somewhat slowly to the desired distribution. And both these downsides came from one property, that Gibbs is doing kind of local and small steps in the sample space. In this video, we're going to discuss some other scheme to build Markov chains, which instead of producing just one predefined Markov chain, will give you a whole family of Markov chains. And you can choose the one that has the desired properties, like it converges faster, or maybe it produces less correlated samples. This family of techniques is called Metropolis-Hastings. And the idea is to apply the rejection sampling idea to Markov chains. So let's start with some Markov chain, which maybe doesn't have anything to do with the desired distribution P. But on the bright side, this Markov chain Q is kind of roll freely in the sample space. It's doing very large steps, and thus it can converge faster, and it produces almost uncorrelated samples. So it's a nice Markov chain, but it doesn't produce us what we want, the samples from the distribution P. And now let's introduce a critic. And a critic is something that says, wait a minute, you can't go there right now. So please stay where you are and wait until you generate some reasonable direction to go. And the critic makes sure that the Markov chain we have doesn't go in some regions where the probability of our desired distribution P is low. Well, at least it doesn't go there too often. And we will accept the proposal, the generated sample from the transition probability of the Markov chain Q with probability given by the critic, and otherwise we will reject, and we will stay where we were at the previous iteration. So this is the general idea, and we will, in the following parts, we will discuss how to build such a critic for a given Markov chain Q and the desired distribution P. So first, let's discuss how this overall scheme will look like in terms of a Markov chain. So we had some Markov chain Q, and we changed its procedure to generate points. And so now this overall scheme generates us points like this. It transitions from the point x to x prime with probability. Well, first of all, we need to generate this x prime from the proposal distribution Q, from the first Markov chain Q, and then we have to accept this point. And this happens with probability given by the critic, so a of x to x prime. This is true for all points that are not equal, so if x is not equal to x prime. And if they're equal, we have something a little bit more complicated, because we again could have proposed to move to x and then accepted this proposal, or we can propose to move anywhere else and then reject that proposal, which happens with probability 1 minus the probability given by the critic, minus acceptance probability. So this is the transition probability of overall Markov chain defined by the process where we propose some points and then accept them with some probability. And now we want our Markov chain to generate points from the desired distribution. So we want some distribution pi to be stationary for this Markov chain T. And the idea here is to let alone the choice of the underlying Markov chain Q. So give this freedom to the user of the method and try to choose A such that this equality holds. So we have as input the Markov chain Q and the desired distribution pi. And we want to choose the critic such that the distribution pi is indeed stationary for the final Markov chain T. How can we do it? Well, it's not easy, because this equation is kind of complicated. It has summation inside and this complicated definition of the transition probability T. So to solve this problem, we'll have to introduce one more concept, which is called detailed balance equation. So recall the definition of the stationary distribution. It's like this. And the detailed balance equation is the following equation, which gives you a sufficient condition for the stationary distribution. So if detailed balance holds, then the distribution pi is necessarily a stationary one for the current transition probability t. And what does the detailed balance equation says us? Well, it says that if we started from the distribution pi and made one time step of our Markov chain t, then the probability that we started from x and moved to x prime is the same as doing the reverse. It's the same as starting from x prime and moving to x. And if it's true, then the probability distribution pi is stationary for t. And it's kind of easy to prove. So let's just, write down the definition, the right-hand side of the definition of the stationary distribution, and then substitute inside that definition, substitute pi of x times the transition probability by the first equation, by the detailed balance equation. And thus we will get summation with respect to x of this expression, and the pi of x prime doesn't depend on x at all. So we can move pi of x prime outside the summation to get something like this. And finally, summation of t of x prime to x with respect to x is just 1. Because this is some kind of probability distribution. And if we sum out all possible outcomes, it will be 1. So finally, we have proven that if the detailed balance holds, then this distribution is necessarily a stationary one. Okay, so returning to our problem, we have a Markov chain Q, which doesn't produce us samples which we want, and we have a distribution pi which we want to sample from. Now we want to define a critic such that the distribution, such that the Markov chain that was created by this critic, so the Markov chain T, will indeed produce samples from the distribution pi. So the distribution pi is stationary. And since this property is hard to check, instead we're going to just check that the distribution pi will be, the detailed balance equation will be true for it. So in the next video, we're going to use Blackboard to find the critic such that this detailed balance equation holds for the given Markov chain Q and the distribution pi. So let's choose the critic. Let's choose the probability A that will, with which probability we will accept a move proposed by Markov chain Q. And let's choose it in the way that the detailed balance equation holds. So here we have the desired distribution pi, which we want to sample from, and we have the Markov chain Q, which we want to fix by a critic A. And we want to fix this A such that this detailed balance equation holds, so pi is indeed a stationary distribution for the Markov chain T, and thus the Markov chain T converges to this pi from any starting point. So let's see how can we choose A such that this property holds. Let's decompose this equality and move all the parts that depends on A in one part. So A of x to x prime divided by A of x prime to x equals to the following ratio. So we have on the one side we have pi of x prime and the q of x prime to x, and in the denominator we have the same thing but with swapping x and x prime. So this is something computable, right? we know pi and q, so we can compute this thing for any two values. Let's call this ratio ρ. Let's assume for a moment that this ρ is less than 1. So it's always greater than 0 because it's some ratio of probabilities, but let's assume that it's also less than 1. So it's just an assumption. It may not hold true, but let's assume that. In this case, we have ratio of a's, which should be equal to ρ, which is less than 1. So let's just use a of x to x prime to be ρ, and a of x prime to x to be 1. This way, the desired equation will hold true, right? Because a of x prime to x to x prime divided by x prime to x will be indeed ρ. And you may notice that we could have chosen here some other numbers, like ρ divided by 2, for example, and 1 divided by 2. But this will also work. The overall Markov chain will indeed converge to the true distribution, but it will be just less efficient. Because this thing is the probability we accept the move. And by decreasing this probability, we will necessarily reject more moves. So we'll waste more capacity of our model on generating moves which we will reject. So this choice is the maximum acceptance probability we can make here while keeping the ratio to be ρ. And what to do if the ratio is greater than 1? Well, we can just choose to be a of x prime, x to x prime to be 1 divided by ρ, and this thing to be 1 again. So we can summarize these two cases where ρ is less than 1 and the ρ is greater than 1 in the following expression. So we can set a of x prime of x to x prime to be equal to minimum between two values, 1 and this ratio. So, and pi of x prime times q of x prime to x and the same thing while changing the parameters x to x prime and vice versa. So this expression works both for the case there with ratio is less than none and less than 1 and greater than 1. You can check it by considering two cases. And in one case it will be just 1 because it's minimum between 1 and something greater than 1. In other cases it will be ρ. So this works, and by choosing this critic we indeed can prove that the overall Markov chain defined by this kind of Metropolis-Hastings procedure will indeed follow this detailed balance equation. So the distribution pi will be stationary for our Markov chain, and we will converge to this distribution pi for any starting point. Thus, by choosing this critic, we may indeed sample from the desired distribution pi. To summarize the Metropolis-Hastings approach to building a Markov chain that converges to the desired distribution pi, we have to start with some Markov chain Q, which may not have anything to do with the distribution pi. And then this Markov chain on each step will propose some moves, and we will have a critic which sometimes rejects these moves and ask the Markov chain to stay where it was at the previous iteration. And we have just proved that if you define your critic to be like this, if your acceptance probability will be this expression, minimum between 1 and some ratio, then no matter from which Markov chain Q you started with, you will necessarily converge to the desired distribution pi. Note that this acceptance probability, it's the only place where we use our distribution pi, which we want to sample from. And note that we don't have to know the distribution pi up exactly. We may know it up to normalization constant. Because here we have a ratio between our distribution at two different points. And it doesn't matter how we normalize this distribution. The ratio will not care about the normalization. Because if we divide each of the parts of this ratio by the normalization constant z, nothing will change. So this method, as well as the Gibbs sampling, can be used when you don't know the normalization constant of your distribution. We have discussed that we can choose Q to be anything, any distribution we want. Well, obviously the Q should be non-zero anywhere, so the ratio will be well defined. But of course the efficiency of and the properties of your overall algorithm will depend on the choice of Q. And there are kind of two opposing forces here. So first of all, Q should make large steps. It should spread out and kind of roll freely in the sample space to make the samples less correlated and to converge faster. On the other hand, if you have too large steps, your critic will reject them too often, and you will waste your capacity by staying at the same place for too long. Because if you're now, for example, already converged and you're in the high density region, then if your Q proposes always to make too large moves, then you will move outside your high density region, and the critic will not be happy with that. It will say like, I don't want to go there. The probability distribution we care about doesn't work, is not high in that region. So in the next video, we'll see some small demo of how this approach can work in one-dimensional case. Let's see how the metropolis Hastings can work in a simple one-dimensional case. Again, it's not that useful in one dimension, but it's chosen just for illustrational purposes. So let's say we want to sample from this two-model distribution the blue curve. And let's say we start with the orange point, which is at the position 0. And it's at the iteration 0. So it's our initialization. Let's see how the metropolis Hastings works here. First of all, let's choose the proposal distribution Q. And to make everything simpler, let's just use standard normal centered around the current point. So at each iteration, the Markov chain Q will propose to move somewhere around the current point with some small variance 1. And for example, at the first iteration, the Markov chain may propose this point, which is a red one. So now we have to compute the acceptance probability, so whether we want to accept this point or not. This is the definition of the acceptance probability we have just proved in the previous video. But note that in this case, the ratio we have, so the Q of x to x prime and the Q of x prime to x, just the same. So it is the property of our current proposal distribution Q that it doesn't depend on the order of arguments, which means that we can just vanish this Q, and what is left is just the ratio of the densities at the new point and at the previous one, which kind of makes sense. It just says that if the new point is more probable than the previous one, we'll definitely accept it with probability 1. If it's not the case, then we will think, like, maybe we'll accept it, but maybe not, depending on how less probable the new point is than the previous one. So in this particular case, for this particular red dot proposal, the new point is much more probable than the previous one. It's like almost 4 times more probable, which means that the probability of acceptance here is 1, and we will definitely keep this point. So the end of iteration 1 is moving to this new point. Okay, what about iteration 2? Let's sample again a point from the proposal, and it will be somewhere around here, for example. Again, computing the acceptance probability. Here we moved a little bit to the higher density region. It's not that much higher, but since it's higher, then we will definitely accept this point. So with probability 1, we are keeping this point. Okay, new proposal. This one is trying to move to a really non-probable region, according to the blue curve. So we'll keep this point with probability point 13. And now we're flipping a bias coin with probability 13, which tells us to accept this point, and with probability 87 to reject this point. So we flipped our bias coin, and it told us to, in this particular example, to reject this point. Okay, why not? Another proposal, it asks us to move here, and this thing is much more probable than the previous one, and we'll keep this point with probability 73. So most definitely keep this one. Again, we're flipping the biased coin, and now it says us again to reject the point. Well, why not? It happens sometimes. It was more probable to accept it, but we happened to reject it. So again, we're staying at the same place we were at the previous iteration. And finally, if you repeat this process for long enough, you'll get a log like this. So you will move in your sample space, and here we have like 50 iterations, and sometimes you will stuck at the same place, and this plot will become flat, but generally you will move around, and you can plot the histogram of the generated points, and it looks kind of close to the Gaussian you want to sample from. So in this case, we didn't get exactly the samples we wanted. The histogram is not exactly like the Gaussian. I'm sorry, it's not the Gaussian, but the blue curve, but it's close. So it's a reasonable way to sample from the blue curve in this particular case. Now the question is, what happens if we change our proposal? So let's say we used a Gaussian with less variance. So we propose always to move just with tiny little steps around the previous point. Well, it kind of works, but in 50 iterations it doesn't proceed to move outside the low density region where it started. So in 50 iterations it haven't converged yet, and it will definitely converge at some point, but we don't know when. And this means that it's much less efficient choice here to use these small steps. What about large steps? Well, if we increase the variance of our proposal distribution Q to be 100, then we will get large steps, which is nice in terms of convergence and uncorrelated samples, but we'll stay at the same place for really long periods, because it will be often then we stay at the nice place, at the highly probable place, and the Markov chain Q proposes us to move far away from it, and we don't like it, so we stay where we were. And this means that our actual samples will be kind of correlated, because we always stay at the same place and we waste the resources and capacity of our computers. I wanted to share with you one more thing about the Metropolis-Hastings approach. It's a really cool perspective on it, which tells us that Metropolis-Hastings can be considered as a correction scheme. So if you have a slightly wrong version of your sampling algorithm, you can correct it with Metropolis-Hastings. Let's look at one example. So recall the Gibbs scheme, the Gibbs sampling. We used to sample points at one dimension at a time, and the Gibbs scheme is inherently not parallel. So we have to know all the information from the previous substeps to make the next substep. Okay, let's try to make it parallel. Let's, just let's break the Gibbs sampling scheme and use the information from the previous iteration, so to not depend. So the substeps will not depend on each other. This way, if we have like million-dimensional space, and if we have million computers, we can do every substeps in parallel, and it will be really, really fast. But the problem is that we broke our scheme. We no longer have any convergence guarantees that it will converge to the true distribution which we want. And it will not actually, so it will generate samples from some wrong distribution. What can we do here? Well, we can use this thing as a proposal distribution for the Metropolis-Hastings, and then correct it with the critic from the Metropolis-Hastings approach. And since this particular proposal distribution is not arbitrary, it's already almost right, almost generating you points from the desired distribution, then you will not reject too many points, because it's already almost the thing you want to do. So you will just occasionally reject one point or another, but generally it may be much more efficient overall, because now you can do Gibbs sampling in parallel. So to summarize, Metropolis-Hastings approach is rejection sampling idea applied to Markov chains. And the nice thing about this approach is that it gives you a whole family of Markov chains, and you can choose the one that you like. Another bright property of this algorithm is that it works for unnormalized probabilities and densities, as well as the Gibbs sampling. And it's also kind of easy to implement. A little bit harder than the Gibbs sampling maybe, but anyway, it's like 5 lines of code in Python. And the negative features are that samples are less correlated but still sound that correlated, and also the property that it gives you a whole family of Markov chains is kind of a two-sided thing. So first of all, it gives you flexibility to choose the right thing for your particular problem, but second of all, it forces you to think, it forces you to choose something, and it may be hard in some cases, and it's harder to automate. So Gibbs sampling works always. You don't have to think at any point. You can just automate the whole process. And to apply Metropolis-Hastings, you usually have to think a little bit and understand which proposal will make sense for your particular application. So let's summarize what we learned so far. We discussed Markov chain Monte Carlo methods, and the Monte Carlo part is about approximating expected values via sampling. And the main question here is how to sample. How can we generate samples from a complicated distribution, which we may know up to normalization constant, which usually happens in probabilistic modeling. To do that, we discussed 2 main methods. Both of them are coming from the Markov chain Monte Carlo family. And the idea of Markov chain Monte Carlo is to build a dynamic system such that if you simulate it long enough, its states start to look like samples from a desired distribution. And this dynamic system called Markov chain, and we discussed 2 ways to build a Markov chain that converges to your distribution you want to sample from. The first method here is Gibbs sampling, which reduces the problem of sampling from multidimensional distribution to a sequence of one-dimensional samplings. And one-dimensional samplings are usually much easier because there are, first of all, some efficient methods for one-dimensional samplings, like general purpose methods, like rejection sampling. Second of all, sometimes you can even compute the normalization constant, because integrating things in one dimension is much easier. And finally, sometimes you can even find analytical solutions to this one-dimensional sampling problem. If your original multidimensional sampling is structured enough. But we discussed some downsides of this Gibbs sampling, is that it generates highly correlated updates. And this means that it converges slowly and that you have to use lots and lots of samples to approximate your expected value accurately enough. The second method we discussed here is Metropolis-Hastings. And it gives you a whole family of Markov chains, which are all converged to the desired distribution you want. And it kind of gives you more freedom, you can choose, right? But with this freedom comes great responsibility. You have to choose wisely. If you choose this Markov chain to be not well suited for your purpose, like if you choose Markov chain that converges slowly or has, again, highly correlated samples, then you will waste lots of resources and the method overall will not be very efficient. So let's put this Markov chain Monte Carlo methods in the context. Let's compare it to the variational inference we covered in the previous week. Again, the Monte Carlo is about approximating the expected values. So substituting them with average with respect to samples you obtain from your distribution. And the main property here is that this approximation is unbiased. So the more you wait, the more accuracy you get. And you can get this accuracy as low as you want if you're willing to wait long enough. And if you want to express this property a little bit more mathematically, you can write down it like this. So this average, this approximation is a random variable itself, right? So if you repeat this process of obtaining samples and then averaging them to get an approximation, you'll get another approximation. So it's a random variable, and it will give you different approximations on different samples. And an estimator like this is called unbiased if its expected value is equal to the thing you want to approximate. So on average, your approximation is correct. And if you wait long enough, this approximation will converge to the right answer. And this is something that is not true for variational inference. So in variational inference, we're trying to approximate a distribution we want to sample from, or we want to work with a distribution from some simple family, like, for example, a family of factorized distributions. And of course, in iterations, variational inference will become better and better, because you are obtaining better and better approximation of your distribution in this class of factorized distributions. But you can't get your error to zero, because you can never approximate your complicated distribution arbitrarily well with a factorized one. So a typical picture of describing this situation is like this. You have your problem and you're trying to solve it with Markov chain Monte Carlo, and it kind of works and gives you a solution which is better and better and better with time, and it's approaching to zero error. Then you use variational inference. It usually gives you a nice solution much faster, but it stagnates. It can't get past some critical value of error and can't get you to zero. So we can, to put this Markov chain Monte Carlo even more in the context, we can recall the table we had in the end of week 3 about variational inference. The table of approximate methods to solve probabilistic modeling problems we have covered so far. So first of all, there is full Bayesian inference, where you model all your parameters and latent variables as latent variables. So you don't train anything in the usual sense. You're not trying to find the best values for parameters, but instead you're trying to marginalize out everything you don't know. And this you theoretically get the best results. But on most practical models, this full Bayesian inference is infeasible, and you have to do some approximations. And one of them is to do mean field, or variational inference, where you assume that your posterior distribution is factorized, and you're trying to approximate your posterior distribution in this factorized family as well as you can. Now we have just added one more method here. We can approximate this full Bayesian inference by sampling from the posterior distribution, and using these samples to estimate the values you care about. So we can use Gibbs sampling or Metropolis Hastings here and sample a few points from the posterior distribution, so from the all latent variables, and then use them to approximate. Then if you can't do even that, or if you don't want to because it works too slow, you can use the expectation maximization algorithm, which basically tries to find the maximum likelihood estimation on the parameters theta. So it doesn't treat theta as latent variable, but instead it treats theta as parameters, and is trying to find the best value for these parameters by using some iterative scheme. And this expectation maximization algorithm is also sometimes intractable. So sometimes it's very hard to do E or M step. And in these cases, you can do again mean field variational inference applied to expectation maximization. So basically on the E step, you can approximate your posterior, your variational distribution Q, with a factorized one. Or again, you can do Markov chain Monte Carlo for AM. So on the M step, instead of working with a distribution Q directly and trying to find expected value with respect to this distribution, you can acquire samples from this distribution, from this posterior on the latent variables, and then use the samples to approximate the expected value on the M step, and maximize this expected value maximize this approximation instead of the original expected value. As the final summary, Markov chain Monte Carlo is a method that allows you to do training or inference in probabilistic models, and it's really easy to implement. It's really easy to parallelize, at least in terms of like if you have 100 computers, you can run 100 independent keep samplers, for example, on each computer, and then combine the samples obtained from all these servers. And finally, it gives you unbiased estimates. So in principle, if you wait long enough, you can get as low accuracy as you may want. And on the negative side, sometimes these Markov chain Monte Carlo methods are slower than the others. But because they're so widely applicable, sometimes it's just the only choice you have. So in the next videos, we will cover a few practical examples of how can you apply Markov chain Monte Carlo to your problems. So let's discuss how can we apply Markov chain Monte Carlo to train latent Dirichlet allocation model, or LDA for short. We have already discussed LDA model in the previous week on variational inference and derived some complicated formulas to do the training in the LDA model. But now let's see how can Markov chain Monte Carlo be applied to the same problem and what are the pros and cons of this approach. So recall that LDA model is a model to find topics in a corpus of documents. And the idea of LDA is that each document has a distribution over topics. For example, one document has a distribution, can be like 80% about cats and 20% about dogs. And then each topic is a distribution over words. For example, topic about cats can in principle generate you any word, but it is much more likely to generate words like cat or meow than others. And so when we look at a particular document, for example, cat meowed on the dog, then we can imagine that this document was generated as follows. First of all, we decided on which distribution over topics we will use. And so here it's 84 cats and 24 dogs. And then we decided that for each word, we must decide on a topic. So for the first word, we may flip by a coin, and with probability 80% it will be cats. And so for the first word, we happen to generate the topic cats. And now we have to generate the first word itself. So we know the topic, now we have to generate the word. And now we can generate any word from our dictionary. But we happen to generate the word cat as the first one. And then we repeat, and when we again sample topic for the second word, and let's say it again happened to be cats, and then let's say we generated the word meow. And then for the last word, let's say we happen to generate the topic dogs and to generate the word dog. Notice that for this model, the order of words doesn't matter. So it's kind of a back of words approach. But anyway, the model is flexible enough to discover meaningful topics in the documents. And so if you put it a little bit more mathematically, you can say that each document has a distribution over topics, theta d. So our document D has a distribution theta d, which is 80 and 20 in this case. And each word has a topic, which we don't know. It's a latent variable. But for like words from 1 to n, ZDI is the topic of the ith word in the document D. And these topics are generated from the distribution theta d. And now each word itself is generated from the appropriate topic. So if the first topic is about cats, then we generate the word 1 from the topic cats, from the distribution for the topic cats. And this distribution is called phi. So phi cats is the distribution over words for the topic cats. And thus we generate the words themselves, which we observe and use to train our model, to find all the necessary latent variables and parameters. And in the variational inference week, we discussed how to use expectation maximization algorithm to train this LDA model. So on the E step, we tried to find the posterior on the latent variables, Z and theta, but it was too hard to do analytically, so we decided to approximate. We decided to find posterior in the approximation of the posterior in the family of factorized distribution, which is the idea of variational inference. And then on the M step, we maximized some expected value of logarithm of the joint probability with respect to this approximate posterior distribution. And we spent quite a few time to derive the necessary formulas and to find a good solution, to find analytical formulas for E and M steps for this EM algorithm for LDA. So if you summarize the model we have here for LDA, we have known data W, which is words in our documents. We have unknown parameters, phi, the distribution over words for each topic, and we have unknown latent variables, Z and theta. So for each word, Z gives us the topic of this word, and for each document, the theta gives us the distribution over topics for this document. And it kind of makes sense that we decided that phi would be parameter and Z and theta will be latent variables. Because the number of Z and theta, the number of variables Z and theta, depends on the amount of training data we have. So for each document, we have to add one new theta and a set of new Zs. So it makes sense to make it in latent variables. So our parameterization will not grow with respect to the training data size. But phi, it has fixed size, number of topics times the number of words in the dictionary. So we made it parameters in our variational inference approach to LDA. But let's see how can we deal with this model if we go fully Bayesian. So if we treat phi as a latent variable itself. So now we don't have any parameters at all. We don't want to estimate any numbers, but we want to marginalize out all the latent variables and to do predictions about some things. So we will apply a Markov chain Monte Carlo to this model of full Bayesian inference for LDA. Although we could have applied Markov chain Monte Carlo to the EM algorithm, but let's just use this full Bayesian model as an illustration. So if we want to apply Markov chain Monte Carlo, we just need to sample all the latent variables from the posterior distribution. For example, by using the Gibbs sampling. So if we want to use Gibbs sampling, we will start with some initialization of all our latent variables, and then we will sample the first coordinate of the first iteration of the latent variable phi from a conditional distribution conditioned on the initialized variables. Then we will do the same thing for the second coordinate, and we will condition on the dimension we just generated on the previous substep, and also on the stuff we have from initialization. And then we will repeat it in iterations to obtain the full phi, and we will do the same thing for theta and z. So for theta, we will generate its ith coordinate at by considering the conditional distribution on theta I, given all the phi's we have already generated and all the thetas we have already generated, and the initial values for the rest of the thetas and for the z. And the same thing for the z. So this is usually Gibbs sampling. It's really easy. I mean, you can implement it like 5 lines of Python. Nothing complicated here, and we will do it in iterations to get like a few hundreds of iterations of this Gibbs sampling, wait until convergence, and then obtain a sample from the desired posterior distribution. Once we have at least one sample from this posterior, we can just use it as an estimation of our parameters. So one sample from the posterior on phi, for example, can be used as just the train value of phi. Or you can average a few phi's if you want. Or you can maybe make predictions with average a few phi's. So you can use these samples to do almost anything with your model. Okay, so you can do that. It's really easy. But the problem is that it will not be very efficient. So compared to variational inference, this approach will not be very fast. And let's see what can we do about it to make it faster in this particular case. So the idea here is to look closely at the model and try to marginalize something out. So basically Gibbs sampling is trying to integrate something, right? So we're substituting expected value, which is an integral, with Monte Carlo samples. And if we can integrate out some parts analytically and then use Monte Carlo only for the rest, then the whole scheme will probably be more efficient. So let's see if we can integrate out some parts of the model analytically. This is the model. We have prior distribution on theta, and theta is just probabilities for topics for each document. So for example, theta for the first document may be 80 and 20. 80 for cats and 20 for dogs. And we have a prior distribution in this theta being Dirichlet distribution, which is natural. I mean, it's the standard prior on this kind of probability random variable, which is probabilities for categorical random variable. Then we have a conditional distribution, z given theta, which is just theta itself. So some topic of some word will be, for example, cats with probability theta cats. Okay, let's see what can we do about this model. So first of all, notice that these two distributions are conjugate, which basically means that we can find the posterior on theta analytically. And it's really easy. I mean, you can look up the formulas on Wikipedia, or you can just derive them yourself, but nothing complicated here because of the conjugate distributions. Then we may try to marginalize out theta. So we may try to find this marginal distribution on z. And it looks complicated. It has an integral inside. But it turns out that since we have the posterior distribution on theta, we can represent it in this way. So this formula comes just from the definition of the conditional probability. If you multiply both sizes by the probability of theta given z, you get the usual definition of conditional probability. And now you have on the right hand side, you know all the terms. You know the likelihood, P of z given theta, is just theta itself. You know the prior, P of theta is just Dirichlet distribution. And you know the posterior, because the distributions are conjugate and you can compute it. So these things are easy. Now you can do the same thing with phi and w. So you can notice that the prior distribution on phi is conjugate to the conditional distribution on w. And thus you can easily obtain the posterior distribution on phi. In the same way you can marginalize out phi. So you can find w given z by using this formula without any integration, because you know the posterior analytically. And finally, you can multiply P of z times P of w given z to obtain a normalized version of the posterior on z given your data. And now everything that left is you may, for example, sample from this posterior distribution. Notice that we don't know actually the posterior exactly, because we don't know the normalization constant, and it's really expensive to compute. But it doesn't matter for Gibbs sampling. We may sample from z anyway. And this will give us a very efficient scheme, which is called collapse Gibbs sampling, because we collapse some of the latent variables and marginalize them out analytically. So this approach will allow you to sample only z's and then obtain and thus make a more efficient procedure overall. And you may ask, like, if I have samples only from the posterior on z, how can I find the values of phi, for example? So something I care about. Well, because you know all the posterior distributions, you can obtain these kind of things easily from the samples from the posterior on z. So the probability of phi given w, for example, which you may be interested in, is can be computed by marginalizing out z from the posterior distribution phi given w and z. And this is some expected value with respect to the posterior on z given w. So you can obtain this thing from samples, right? You can sample a few z's from this posterior distribution and then average them to get this estimation of the posterior distribution on phi, and get the actual parameters phi, which corresponds to the probabilities of each word for each topic. If you're willing to know more details about this kind of collapse Gibbs sampling for LDA, look into the original paper that introduced that. It's really cool. So check out the additional reading material if you're interested. But the bottom line here is that if you run this collapse Gibbs sampling for the LDA, it will be even a little bit more efficient than variational inference. So here on the plot you can see the basically time on the x-axis, or number of operations we performed, and some measure of error on the y-axis. So the lower, the better. And you can see that Gibbs sampling is performing a little bit better than variational inference, and also better than something called EP, or expectation propagation, which we will not talk about in this course. And the bottom line here is that we were able to obtain a really efficient scheme for solving LDA model without too much trouble of variational inference. So we didn't have to derive a large number of complicated formulas. We just applied the usual scheme of Gibbs sampling. It wasn't very efficient, and then we just marginalized out some parts analytically, which was also really easy, and we finally got an efficient scheme for LDA. And one more thing here is that generally Markov chain Monte Carlo is not very good suited for mini batches, so for large data. It has to process the whole data set on each iteration. But sometimes it works. So you lose all the guarantees of Markov chain Monte Carlo when you use mini batches, and sometimes it fails miserably. But in this case, the authors just used mini batches, and it works quite nice here. In the last video of this week, let's discuss how can we apply Markov chain Monte Carlo to Bayesian neural networks. So this is your usual neural network, and it has weights on each edge, right? So each connection has some weights which we train during basically fitting our neural network into data. Bayesian neural networks, instead of weights, they have distributions on weights. So we treat W, the weights, as a latent variable, and then to do predictions we marginalize W out. And this way, instead of just hard set value for W11, like 3, we'll have a distribution on W, a posterior distribution which we'll use to obtain the predictions. And so, to make a prediction for a new data object X, and using the training data set of objects X train and Y train, we do the following. We say that this thing equals to integral, where we marginalize out W. So we consider all possible values for the weights W, and we average the predictions with respect to them. So here, your P of Y given X and W is your usual neural network output. So it's you have your image X, for example, and you pass it through your neural network with parameters W. And then you record its predictions. And you do that for all possible values for the parameters W. So there are infinitely many values for W, and for each of them you pass your image through the corresponding neural network and write down the prediction. And then you average all these predictions with weights, where weights are the posterior distribution on W, which basically says us how probable is that this particular W was according to the training data set. So you have kind of an infinitely large ensemble of neural networks with all possible weights, and with basically importance being proportional to the posterior distribution on W. And this is full Bayesian inference applied to neural networks, and this way we can get some benefits from probabilistic programming in neural networks. So we can estimate uncertainty, we may tune some hyperparameters naturally, and stuff like that. And so we may notice here that this prediction, this integral, equals to an expected value of your output of your neural network with respect to the posterior distribution on W. So basically it's an expected output of your neural network with weights defined by the posterior. And so to solve this problem, let's use your favorite Markov chain Monte Carlo procedure. So let's approximate this expected value with sampling, for example with Gibbs sampling. And if we acquire a few samples from the posterior distribution on W, we can use that W's, that weights of neural networks, and then if we have, like, for example, 10 samples, for each sample is a neural network, is a weight for some neural network, and then for a new image we can just pass it through all these 10 neural networks and then average their predictions to get approximation of this full Bayesian inference with an integral. And how can we sample from the posterior? Well, we know it up to normalization constant, as usually. So here this posterior distribution on W is proportional to the likelihood, so basically the prediction of neural network on the training dataset with parameters W, times the prior, P of W, which you can define as you wish. For example, just a standard normal distribution. And you have to divide by normalization constant, which you don't know, but it's okay because Gibbs sampling doesn't care, right? So it's a valid approach, but the problem here is that Gibbs sampling, or Metropolis-Hastings sampling for that matter, it depends on the whole dataset to make its steps, right? We discussed at the end of the previous video that sometimes Gibbs sampling is okay with using mini batches to make moves, but sometimes it's not. And as far as I know, in Bayesian neural networks, it's not a good idea to use Gibbs sampling with mini batches. So we have to do something else. If we don't want to, when we run our Bayesian neural network on a large data set, we don't want to spend time proportional to the size of the whole large data set at each iteration of training. We want to avoid that. So let's see what else can we do. And here comes the really nice idea of something called Langevin Monte Carlo. And this is basically, so it works as follows. Say we want to sample from the posterior distribution P of W given some data. So training data X train and Y train. Let's start from some initial value for the weights W. And then in iterations, do updates like this. So here we update our W to be our previous W plus epsilon, which is kind of a learning rate, times gradient of our logarithm of the posterior, plus some random noise. So the first part of this expression is actually a usual gradient ascent applied to train the weights of your neural network. And you can see it here clearly. So if you look at your posterior P of W given data, it will be proportional to logarithm of prior plus logarithm of the conditional distribution, P of Y given X and W. And you can rewrite it as follows by using the property of logarithm that, like logarithm of multiplication is sum of logarithms. And you should also have normalization constant here, Z, but it's a constant with respect to our optimization problem, so we don't care about it, right? And on practice, this first term, the prior, if you took the logarithm of a standard normal distribution, for example, you just get some constant times the Euclidean norm of your weights W. So it's your usual weight decay, which people oftenly use in neural networks. And the second term is usual cross entropy, usual objective that people use to train neural networks. So this particular update is actually a gradient descent or ascent with step size epsilon applied to your neural network to find the best possible values for parameters. But on each iteration, you add some Gaussian noise with variance being epsilon, so proportional to your learning rate. And if you do that, and if you choose your learning rate to be infinitely small, you can prove that this procedure will eventually generate you a sample from the desired distribution P of W given data. So basically, if you omit the noise, you will just have a usual gradient ascent. And if you use infinitely small learning rate, then you will definitely go to just the local maximum around the current point, right? But if you add the noise on each iteration, theoretically you can end up in any point in the parameter space, like any point, right? But of course, with more probability, you will end up somewhere around the local maximum. If you're doing that, you will actually sample from the posterior distribution. So you will end up in points with high probability, more often than in points with low probability. On practice, you will never use infinitely small learning rate, of course. But one thing you can do about it is to correct this scheme with Metropolis-Hastings. So you can say that theoretically I should use infinitely small learning rate. I use not infinitely small, but like 0.1. So I have to correct. I'm sampling from the wrong distribution. And I can do Metropolis-Hastings correction to reject some of the moves and then to guarantee that I will sample from the correct distribution. But since we want to do some large-scale optimization here, and to work with mini batches, we will not use this Metropolis-Hastings correction because it's not scalable. And we will just use small learning rate and hope for the best. So this way we will not actually generate samples from the true posterior distribution W, but it will be close enough if your learning rate is small enough. So it's close enough to the infinitely small, right? So the overall scheme is as follows. We initialize some weights of your neural network. Then we do a few iterations or epochs of your favorite SGD. But on each iteration, you add some noise, some Gaussian noise with variance being equal to the learning rate, to your update. And notice here also that you can't change learning rate at all at any stage of your sampling, or you will also break the properties of this Langevin Monte Carlo idea. And then after doing a few iterations, like 100 of them, you may say that, okay, I believe that now I have already converged. So let's collect the following samples and use them as actual samples from the posterior distribution. Okay, this is the usual idea of Monte Carlo. And then finally, for a new point, you can just average the predictions of your 100 slightly different neural networks on this new object to get the prediction for your object. But this is really expensive, right? So there is this really nice and cool idea that we can use a separate neural network that will approximate the behavior of this ensemble. So we are simultaneously training this Bayesian neural network, and simultaneously with that we're using its behavior to train a student neural network that will try to mimic the behavior of this Bayesian neural network in the usual one. And so it has quite a few details there on how to do it efficiently, but it's really cool. So if you're interested in these kind of things, check it out.